And now we have this example, which is I just worked through it and put it all here. But actually, I think it might be more interesting to actually work through it with you in my whiteboard to kind of like, you know, test this new thing. So and then I will give you a little bit of an interval. So the only problem is that I might get confused. But anyway, let's see. Let's try this. So basically, okay, let me read this thing before I actually, because when I take my whiteboard, this is going to disappear. So this is from, again, from Khan Academy as always, because I love their examples. So uh, let's work through this, how to build a confidence interval out of some like pseudo realistic example. So Kylie suspected that when people exercise longer, their body temperatures change. I think it's similar to what a couple of you have actually thought about to do the data gathering on. So she randomly assigned people to exercise for 36 minutes. So two different populations, a population of, so to speak, right? Samples of two different populations, two different samples of two different populations. One of people who exercise for 30 minutes, another one for people who exercise 60 minutes. Okay, it's different people, different samples from different populations. Then after that, she measured the temperatures. So there were 18 people who exercised for 30 minutes. So a sample of 18 people, right? And then she measured it, and the mean temperature was this, 38.3 degrees Celsius. And a standard deviation was 0.27 degrees Celsius. Then there was the other sample of 24 people who exercised during 60 minutes. And then she measured the mean temperature of this sample of 25 people, and that was 38.9 degrees Celsius. And the standard deviation was slightly larger, was a 0.29. So it's, the temperature is larger or higher, or actually, but also the standard deviation is a bit higher, so it also varies a little bit more. So it's hard to say that it is for sure higher than the other one, because since it's varying, you have to do a statistical test here to, or build this confidence interval to make sure that actually makes sense to state that the 60 minutes people had higher temperature. And that's what we're gonna do, right? So I'm gonna open this whiteboard here, and I promise that after this I will give you a few minutes to rest. And I'm going to actually replicate at least the most important parts of this thing. So let's see if this works. The sample mean of people who exercise for 30 minutes is 38.3 degrees Celsius. And the standard deviation of this sample of people who exercise 30 minutes was 0.27. Oh, not this. Was 0.27 degrees Celsius. Okay. Then there was this other sample of people who exercised 60 minutes, and the sample mean was 38.9 degrees Celsius. So it was larger, right? The temperature was larger indeed, but it also varied more, which was 0.29 degrees Celsius of standard deviation. So it's hard to affirm for sure that, you know, also of importance here is the n. So we have the sample size was 18 for 30 minutes, and the sample size for 60 minutes was actually 24. So you can see that the sample sizes are not the same, and it doesn't matter. Actually, it doesn't have to be the same, right? Now, what is it that we are trying to compute here? So we want to build a confidence interval that will be, let's call it CI, and this will be basically the difference between the sample means. So let's start with the 60 because it's larger, but it doesn't matter. Actually, it's symmetric, so it doesn't matter. Plus or minus our, whatever it is, our critical value, which we haven't defined yet, right? We haven't defined our confidence level yet, but we will. times the, let's call it the S here of difference. I'm just going to call it like S difference, which is just the standard error of the difference, we're going to compute everything. So this is what we want here, right? This is where we want to get to. This is our, let's say, final goal, right? And I'm just gonna find it here. I'm not sure why I don't see the participant list anymore, and I want to see it. Just a second, because maybe some of you ask questions and then I have to know. Okay, so interrupt me if you need. Okay. Now this is where we want to get to. We want to get this interval plus or minus the mean. So let's see how this goes. First of all, so you know what, I'm gonna actually rewrite this as being the x bar diff. So what's this value that we're estimating? We're estimating difference. So let's call it x bar diff. So it's the difference that we're estimating. Well, the actual difference is simply 38.9 minus 38.3, right? Which is basically 0.6. Now, notice that I did the 61st and the 30, then the 30. It doesn't matter. If you do it the opposite, it's exactly the same, but as long as you're like consistent with this, okay? And I'm about to lose my iPad. Oh my God, let me put it on. Yeah, okay. Now this is the X different, nice, because this is one of the things that we need over here, right? Now, what is our T star? Well, our T star depends on our confidence level and our degrees of freedom. So let's just, I don't know, let's just use a confidence level of 90. Let me see which one I used actually in the, yeah, let's use it. Let's say it's a 95%, or sorry, 90% confidence level. So I'm going to write it here. 90% confidence level. Okay. So I have a 90% confidence level. What does that translate to in terms of T star? Well, I'm going to actually open that same calculator that we used before. And instead of 2.5%, I'm actually going to put 5% now, because I want 5% on the left and 5% on the right, right? It's because it's two-tailed. So I'm using 5% significance level. What is my degrees of freedom? So let's think about this. My degrees of freedom is the minimum sample size, so 18 minus 1. So my degrees of freedom are 17. So I'm going to put it here 17. Now I have basically a 5 significance level, significance level of 5, and 17 degrees of freedom. Then I calculate the T and the T star, and the T star is actually 1.74. So I'm going to go 1.74 to the left of the mean standard errors, 1.74 standard errors to the right of the mean. And as you can see, it's less than 2, because it's, since I only want 90% confidence and not 95 or 99, then it's less than 2. It's slightly shrinked, let's say. Now this is our T stars. Okay, this is the second thing we needed here. And now I need the standard deviation, or the standard error, sorry, of this difference of the means. And then again, I'm gonna go back to my slides here, and I'm gonna look at the formula. And the formula is that I need the, let's say, the S, sorry, not this. Actually, yeah, actually doesn't matter, but I'm just gonna follow the same sequence here. I got the standard deviation of those people who exercise for 60 minutes, uh, divided by the sample size of 60 minutes, which is 24, plus the standard deviation of the people who exercise for 30 minutes squared, divided by 18, which is the sample size for 30. Then I'm going to take the square root of this thing, and I guess this is going to get a little hairy, which is no problem. but I have it here, so I'm just gonna put it here, because I did this before. So this will be 0.29, which is the standard deviation of the 60 minutes, right? Squared, divided by 24, plus 0.27 squared divided by 18, again because this is the standard deviation for the 30. Then I will take the square root, and then this is just numbers, so you just put this in a calculator, and that will be more, not exactly, because this is going to be like a lot of numbers, but more or less approximately to 0.0869. Cool. Okay, so basically we have everything now. So I know the difference that I wanted to measure. I computed my t star, and I also computed the standard deviation of the difference, and that's it. All I need now is to just say, okay, my confidence interval is 0.6 plus or minus 1.74 standard errors times, let's say, oh my god, times times 0.0869, and that makes sense, right? Because 0.6 is in the middle of the distribution. Then I want to go plus or minus something, which is 1.74 times my standard error. So 1.74 standard errors to the left, 1.74 standard errors to the right, and that actually ends up being 0.6 plus or minus 0.1512. Or in other words, you could say, okay, my confidence interval is from 0.4488 to 0.7512, because 0.6 minus the 0.1512 is 0.4488, and 0.6 plus 0.1512 is 0.1712, 7512. Now, and this is it. That's where you are. That's what you need. This is your confidence interval, nothing else. And then what will you say after you get this? You'll say, okay, considering all these information, I can say that I am 90% confident that the true difference between the let's say the average temperatures of these two groups is somewhere between 0.4488 degrees Celsius and 0.7512 degrees Celsius. I mean, and that would be okay. Like you could say, okay, this is my confidence interval, right? But actually, there's one more thing that you can actually conclude from this, which is quite interesting, which is to say, look, the zero is not within this interval. Zero is somewhere over here, right? Zero is less than the lower end of my confidence interval. So I cannot say that zero is within my confidence interval. So basically, I can say I'm pretty sure, or I'm 90% confident that these temperatures are not the same. Because if they were the same, if the true population, if the true value of the difference between these two populations was actually zero, which means that they would be the same, then zero should be inside my confidence interval. It's okay if it was in the middle. It would be okay if it was a little bit to the left or a little bit to the right, as long as it was inside the interval. But it is not. It's outside the interval. So it's basically outside the range of values that I consider to be reasonable to expect. Thus, I can quite confidently say that zero is not one of the possible population values. And but at the same time, I can say that the difference between the means is not zero. So basically, if I'm asking, is X bar 30 equal to X bar 60? Well, is X bar 30 minus X bar 60 equals zero, which is the same, right? They're all both the same. I can very confidently say No, probably not, because 0 is not within the confidence interval.